Welcome everybody. It's a pleasure to speak in front of you, and I'm going to talk about automated particle picking and preprocessing in SPHIRE. And this is done by two standalone tools. One is crYOLO, which is developed by me, and the other one is the automated preprocessing software TranSPHIRE, which is developed by my colleague Markus Deprin. I'm going to start with talking about crYOLO. So particle picking, it's basically common object detection from computer vision. And what you typically do is you set up a training set which consists of positive and negative examples. The positive examples are, in our cases, here TCDA1 toxins. And the negative examples are background, contamination, and so on. And then one popular approach is to use a sliding window. So you train your classifier, and then you use this sliding window, which goes over your input images. You crop out small regions, and you pass it through the classifier. And the classifier will tell you, okay, with a probability of, I don't know, 0.8, this is a particle or a background. And then you put this probability at the position of the window, and you get a confidence map. And the next step is then identify the maximum on the confidence map, and these are your final particles. There is another approach, alternative to the sliding window approach. And instead of passing all the time small cropped out images through the network, it takes a complete micrograph and pass it through the network. And in the end, you get a grid-like result where each grid cell detects or can detect the particle. This approach has some advantages. So for the normal sliding window approach, you typically have to label particles and contaminations and background. For the YOLO approach, you only need to label your particles, not the background. So no negative examples are basically need to be labeled manually. The context is much bigger because in the sliding window you always, the classifier only sees a small cropped out region. And for the YOLO approach, it always sees the complete micrograph. The computational efficiency for the sliding window approach is rather bad because these windows that are passed through the classifier are overlapping. And therefore, it basically looks at the same position multiple times. And for the YOLO approach, this is very efficient. Right now, crYOLO can pick up to 6 micrographs per second. So how is the crYOLO training working? You start with a small training data set of, let's say, 5 to 15 micrographs that you manually labeled. And this is passed multiple times through the network. And each time it's downsized, it's filtered, it's augmented, but this is basically transparent for the user. You don't have to care about it. crYOLO is doing that for you. So, and in the end, if the image is passed through the complete network, you get this stack of grids. And each grid cell is responsible for a small region in the image. And the first, so each layer in this stack of grids has a different purpose. So the first layer, so a grid cell in the first layer basically just classifies, does I contain a particle center, the center of a particle, or does I not contain a particle center? And if this is the case, how confident I am in that there's a particle. And then the third and the fourth layer are estimating the X and Y position, whereas the last two layers are estimating the box width and the box height. The loss function that we are trying to optimize consists of 4 parts. The first two, penalizing errors in the estimation of the actual position of the particle. The second one is penalizing errors in estimating the width and the height of the boxes. And the last two layers are penalizing errors in the confidence values for picking particles or not picking background. So basically false positives and false negatives. The actual training is pretty easy. You put your MRC files into one folder, you put your box files or star files into one folder, you specify the passes to these two folders inside a configuration file called config.json. And then you do a so-called warm-up training, which is only a couple of epochs. And then this warm-up training basically ignores the estimation of the width and the height. And this is just heuristics that the YOLO developers come up with because they say it's converging better if you do it like this. And the third step is the full training. And typically it lasts 15 to 20 epochs until it converges. So for our training set with 10 micrographs on our machines, it was 8 minutes for the complete training, so not too long. If you have more training data, of course it will take more time. But typically you don't need more training data. So in the end, what you get is an H5 file. This is your model. It contains all the weights of the network. This is basically specifies the network. The prediction is even easier. You just specify where are my images that I would like to pick. You give the predict command your model and your configuration file, and you specify where to save the results. And what you get are 3 folders: a star folder, an eman folder with eman2box files, and a so-called cbox folder. Each particle is connected with confidence threshold. And the normal eman2 box files contains the particles with a confidence threshold of 0.3. But it might be that this is not optimal for you, and then you can load in the cbox files and basically choose on the fly with a live preview the threshold that you would like to use. You can increase it or decrease it, and if you are happy with the result, you can just save new box files and use them for further processing. Here are a couple of examples where we applied crYOLO with basically the same configuration, of course different training data, but the same configuration. You are able to pick very big particles like viruses, or small particles, very crowded particles, or you can also pick particles very specifically. And here are shown HIV spikes attached to liposomes, and another example is MPGs attached to liposomes. Another good property of crYOLO is that it's pretty good in ignoring contamination. So if your training data shows contamination, it is able to learn not to pick it. And it does it quite good. So it does not need too many training data to learn that. Typically these 5 to 15 images are enough. One nice feature of crYOLO is that it's tolerant against sparse picking or sparse labeling. If you create your training data set, you often might not be able to pick all the particles to completion because they are not good visible or you're not sure, and so on. But crYOLO still works pretty good. And to illustrate this, what I did was I took our TCDA1 toxin data set, and it consists of 10 micrographs with 1,100 particles labeled. And then I removed 80% of the particles. And what is left are 205 particles on 10 micrographs. And then I trained the model based on this sparsely labeled training set. And if you then run crYOLO, you will realize, oh, it does miss a lot of particles. But here it's shown in the upper right corner. But then the CBOX files becomes handy, because you can simply load the CBOX files, reduce the threshold, and you get all your particles back without running crYOLO again. You just have to reduce the threshold, because obviously if you miss a lot of particles, it's getting a little bit unsecure, and you just have to decrease the threshold for the confidence so you get all your particles back. Here's a more, I try to compare the model trained on the complete data set with the model trained on the sparsely training data set. And what you see here are the so-called precision recall curves. And you calculate the number, is the area under these curves, and if you get a 1, then you have your perfect classifier. If you get a 0, then you have the worst classifier ever. The completely labeled data set achieves a value of 0.95 on the toxin data set, which is excellent. But also the sparsely labeled data got a value of 0.88, which is still very, very good. And we tried this on a couple of other data sets. You can check it out in our wiki page. It seems to work really well. Another thing I would like to highlight is the general model. So typically you will make multiple data acquisitions for the same particle using different cameras, a different microscope, different grids. And it's likely that one model that you trained on only one data set from one data acquisition will not perform perfectly on another data set, which might use a different grid or different settings or whatsoever. But you can get a much better generalizing model if you merge the training data of multiple data acquisitions. And you do it in crYOLO by simply create subfolders into your training folder and put each data acquisition in a separate folder together with the box files, and then you train the model as you do it for a normal data set. You train it in the same way, and what you get is a model that it's much more likely will work on data sets from your next data acquisition without the need to retrain it again. And we created two general models that are available on our website. The more powerful one is the one for cryo-EM, because we simply have more training data for it. It consists of 32 hand-picked real data sets. All of them consist of 20 to 40 images. And we simulated 10 other data sets, and we also added data sets which does not contain any particle, only contamination. And on the right side, you'll see if we apply this model to data sets which are not part of the general model, it still performs pretty good. And we did the same for negative stain images. I put it online a few weeks ago. For our lab, it works. We will see how the feedback is for the negative stain model. For the general model, for cryo-EM data, the feedback is pretty good. But of course, we constantly have to update. Now the case 3 came out, and it will take a while until example images of the case 3 find the way into this general model. The last feature of crYOLO that I will show you is the filament mode. So you train crYOLO using training data generated by the E2 helix boxers by manually labeling your filaments. And what you get are, if you apply then crYOLO, is these red boxes here. And the next step is basically a post-processing step. So in principle, we hacked crYOLO because right now it's not able to directly predict the elongated boxes for filaments. And what we did is we convolved the input image with the mask shown here and we rotate this mask, and where we get the highest response is the direction of the filament, and then we trace the boxes along this direction using the pick boxes of crYOLO as support points in principle. This works really good, and even for more complicated cases where you have a lot of bundles, it works pretty well. But still, I think this is the next thing I would like to work on is it should be possible to make an end-to-end learning out of this, that crYOLO directly predicts the rectangular boxes. This would be much more elegant, and I guess it would be more powerful, because right now I'm failing to generate a general model for filaments, and I guess this is one of the reasons. To summarize, crYOLO is pretty fast. It picks up to 6 micrographs per second. It is pretty good in learning the context, because it always sees a complete micrograph. The training is fairly easy. You only need a couple of micrographs for training, and often it's needless. If you can use the general model, you don't need to train. And the training is tolerant against sparse picking. So if you're not sure in picking your particles, crYOLO doesn't care. It will hopefully still work. Okay, I try to provide a lot of documentation how to use crYOLO, how to create general models, how to use the filament mode in a step-by-step manner. It should be very easy. Check out our preprint, and the final paper will be available soon. The next thing I would like to talk about quickly is TranSPHIRE. So after data acquisition, a lot of things have to be done, like motion core, CDF estimation, particle picking. You have to distribute your data to clusters, GPU boxes, user working machines, and so on. And TranSPHIRE does all of that for you. And it also integrates crYOLO in a nice manner, so you already get your particles picked. It supports multiple tools, like Motion Core 2 for motion correction, GCDF, CDER, CDF Hind 4 for CDF estimation, crYOLO for particle picking, and yeah, it's pretty flexible. The installation is super easy. You just create your Python environment and then install the pip package, so pip install TranSPHIRE, that's it. You set up your microscope computer where the passes and so on. You specify some default settings of your external tools. You only have to do that once. It's saved then, right? It's the first run. And that's it, basically. And for an example, how to use it, you give the folders where the microscope will put the images, and you specify a healthy range of your parameters like defocus and so on, where you might want to get notifications, and then you start the process. And crYOLO will show, TranSPHIRE will show you a lot of information during this process. And basically now on the right side you see how it processes the data in a parallel manner and shows you all the data, all the information on the fly. Maybe the videos was a little bit too fast, but what Marcus tries is to provide simplicity for new users. So he always tries to put it into main advanced settings that new users just see not the whole bunch of parameters that they probably don't need, only the most relevant ones. But at the same time, it should provide all the complexity that is necessary for more advanced users. The last two features I would like to highlight is the automated notifications in case your data acquisition stops, in case your one of the pipeline steps fails, or if some of your parameters are running out of range, TranSPHIRE can send you an email or a messaging app via Telegram. And the second thing is the remote monitoring. You don't have to sit in front of the microscope computer to see what TranSPHIRE is doing. You can go back to your lab computer and still monitor what TranSPHIRE is doing, and in case something went wrong, you can correct it. You will find all the documentation on our website. And all these automated things, crYOLO, automatic pre-processing, paving the way for more fully automated processing. And in the latest release, we included one of the first steps in SPHIRE called AutoSPHIRE. And here we process beta-gal in a completely automated manner up to CTF refinement. And this was done by Marco Stabrin and Christos Gatsagiannis. And yeah, the next steps are automatic 2D class selection and stuff like that. And with this, I would like to thank Stefan Raunzer, our PI, for all the freedom that he provides our team to do the development of SPHIRE. I would like to thank the whole SPHIRE team, especially Marco Stabrin. As I joined the field 2 years ago, I would have been lost without him. And the complete department, which put a lot of effort into create training data for the general model for crYOLO. So it's really a pleasure to work with them. And with this, I would like to thank you for your attention, and I'm open for questions.
Thank you very much, Thorsten. Any questions? There's a question? Oh.
So does crYOLO have problems picking particles with low contrast and low defocus, low molecular weight?
No. What I can tell you from our experience in our lab and what other users are telling me, no, crYOLO has not a problem with picking on low defocus images as soon as you provide training data. So it will probably not work if you only provide high defocus images to train. It will probably not work on low defocus images, but if you also provide some of the low defocus images in the training data, sure, it will work.
Hiya. So you said that when you sparsely train the model, that you then have to you have to play with the threshold to get the good picking back. Do you find that the threshold that you find is then consistent across the whole data set?
No. So at least for the experience that we do, the same threshold that works for the high defocus images is also the same for the low defocus images, if this is what you are asking for.
Yeah, I was just wondering if it was consistent. And do you think there's any value then to the positive unlabeled framework that other people are maybe working in?
Sorry?
Do you think there's much value to the positive unlabeled framework if it's this easy to correct for?
I guess it solves the problem in a very elegant manner. So, of course, this is a cool contribution to the field. But and it might be that this is also the better way of doing it. But what I would like to show is that crYOLO still works, so that's not a problem if you train it with sparsely labeled data.
Perfect, thank you.
Sure.
So did you had a chance to test crYOLO on flexible filaments? So filaments that are helical, but they are not particularly straight?
I mean, the filaments I tested it with were always a little bit bended, like the actin, but I never tried it on very curved filaments. No. So I mean, if they are very curved, it depends if you can at least divide it in small sections into straight lines, then I would expect that it will work, but I can't tell you, I never tried it.
So as the size of your generalized model increases over multiple data sets, is there much overhead when you're running crYOLO? Because your model is...
The computational part is the same. Of course, the training will last for a longer time, but I mean, I train the general model for you. You don't have to train it. So I train the general model. As I told you, 50 data sets, each 20 images. It takes a while. I train for 1 day roughly, but the user don't have to do it, right? The user typically trains on, let's say, 20 images. This is fast.
You mentioned that you'd recommend training the algorithm on multiple data collections from the same protein. If you had a protein that shows like different conformations, or you have mutant forms of the protein that show slightly different conformations, would the trained algorithm on one conformation of the protein be likely to pick up a different conformation? Like how malleable is it to slightly different conformations of the same protein?
I would expect that it depends on how strongly visible is this conformation change in the low frequency features of the particle. I mean, if you have a particle which is most of the time a T-like particle, and then probably you have a stick-like particle because of a conformational change or whatever, it might learn not to pick it. So then you have to actually merge your data sets to get it running.
Okay, I think we'll stop here. Everybody's hungry. We'll come back, I think. We'll come back at 1:30.